The third and final new topic for today's lesson is doing real-world design using Karnaugh maps. And so there are a variety of different real-world problems that Karnaugh maps can contribute to. We're going to kind of restrict ourselves to a particular class of problems because they're relatively easy to analyze, but they're definitely, I think, more interesting and more creative than just solving sort of a generic problem. So what I want you to do is consider this figure right here. We have a modulo 8 counter. It's often just abbreviated as a mod 8 counter. And as soon as you see that it's a binary mod 8 counter, that's enough information to know the exact sequence that counter is going to follow. It's going to say 000, 001, 010, 011, 100, 101, 110, 111. And then after it gets to 111, it will then cycle back to 000 again. Just as a clock counts from 1 to 12 and then returns back to 1 and then goes back up to 12, it's a cycle that repeats itself. So when we say mod 8, what we mean is that there are 1, 2, 3, 4, 5, 6, 7, 8 different numbers. And binary simply means that this is in a binary sequence. If you look at these, this corresponds to a decimal 0, decimal 1, 2, 3, 4, 5, 6, and 7. So 0 through 7 is mod 8. So we have a binary mod 8 counter, which at this moment, you don't know how to design. Eventually, before the end of this semester, you will be able to build a binary mod 8 counter. But for right now, that's beyond our scope. But we do know that because it's a mod 8 counter, it's going to have 3 output bits. We're going to label those as A, B, and C. We're going to send those as inputs into a decoder. And the job of that decoder is to light up an LED when the number ABC is either 0, 2, 4, or 5. Or as you can see up here, this would be 0, 0, 0, 0. 2 would be 0, 1, 0. 4 would be 1, 0, 0. And 5 would be 1, 0, 1. So what we're really specifying here is the combinations of A, B, and C that are supposed to light that LED. And in the text, you can see here that we put it into the context of thinking of these 8 numbers here, 0 through 7, as representing the 8 periods in the academic day. And then these might be the hours in which you have class. So you have an LED that would light if you're in class, for example. Seems like a pretty simple example, but nonetheless, it's one that does have some real-world applications. So what we understand is that we want the light to turn on for combinations of inputs 0, 2, 4, and 5, which is actually very easy to translate into a minterm expression. You just simply say it's the sum of the minterms 0, 2, 4, and 5. And because you didn't mention 1, 3, 6, or 7, it's understood that those are going to be zeros. You don't have class during those class periods. So once you get it down to this minterm expression, you've already seen how to do that. You would then fill in a k-map. We see that this will be a 3-variable k-map, so it's going to be the one that's 4 by 2. You would fill in the cells 0, 2, 4, and 5, do the grouping, write the equations, problem would be solved. So the only thing that's really new here is to go from a picture and a description into this minterm expression. Of course, you could equally well just have written it as a truth table, but I think the minterm at this point is the simpler and more compact way of doing it. Here's another example. In this case, this is a binary modulo 12 counter. Now, a mod 12 counter is going to need 4 bits because if you want 12 different possible combinations, that will not fit into 3 bits. That can only hold 8 different combinations. So we have to go up to 4 bits. Now, 4 bits could actually handle up to 16 different combinations. So if I said that this was a binary mod 16 counter, that'd be easy peasy. You would know exactly what was going to happen with A, B, C, and D. But because this only is a mod 12 counter, that means that it's going to go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. So mod 12 is 0 through 11. But there are 4 other numbers that will never be used. So we have 12, 13, 14, and 15. Those will never be the output sequence because as soon as you get up here to 11, you cycle back to 0 and you go from 0 up to 11, then cycle back to 0. It's a closed loop. And so you will never have 12 as the output or 13 or 14 or 15. Although those numbers would be a possible number that could fit within 4 bits, because you are driving this with a mod 12 counter, that will simply never be the case. Now, if this will never output those numbers, then that means that this will never receive those numbers. So if the mod 12 counter is not going to generate 12, 13, 14, and 15, that means that those input combinations are forbidden from the decoder. They will not forbidden, but they will just simply never happen. So we're asked to light up this LED on the even numbers. So 0, 2, 4, 6, 8, and 10. Of course, there are 2 other even numbers. There's 12 and there's 14, but those will never happen, so we don't need to worry about those. So how do we write this out? Well, it's the sum of the min terms 0, 2, 4, 6, 8, and 10 plus the sum of the don't care min terms 12, 13, 14, and 15. Because 12, 13, 14, and 15 will never occur as input combinations, we don't care what output would correspond to those. So when we fill in this truth table, when we fill in the Carnot map, now we put 1s in cells 0, 2, 4, 6, 8, and 10, and we put x's in cells 12, 13, 14, and 15. Having those x's will allow us to reduce the complexity of our circuit considerably. So that's all there is about advanced Carnot maps. At this point, you're ready to tackle the real-world design problems with K-maps example, and then you're ready to come to class and see some more example problems.